Okay, Assalamualaikum warahmatullahi ta'ala wabarakatuh to everyone. A very good day. So today we continue to the last part and first law of thermodynamics. We discuss on part 3b, also same chapter, energy in steady flow. So previously we have discussed on part 3a. We have talked about the nozzle, the turbine, the pump, and today we will discuss another device that is normally discussed in energy flow. Okay, so we continue with the first, which is throttling valve. So throttling valve are any kind of flow restriction device that cause a significant pressure drop in a fluid. Normally we will find throttling valve in air conditioning system. So the pressure drop in the fluid is often accompanied by a large drop in temperature, and for that reason throttling devices are commonly used in refrigeration and aircon. So in general assumption, there is no heat involved in the throttling valve, and also kinetic and potential energy is also assumed negligible. So for general equation, so no heat, no work, we take out. Also no heat out and no work out, we take out. So also we don't have any kinetic and velocity, we take out. Same mass, we cancel out. So we have only H2 is equal to enthalpy 1. Enthalpy outlet is equal to enthalpy inlet. Also enthalpy, you have kinetic energy 1, internal energy 1 plus pressure 1, volume 1 is equals to internal energy 2 plus pressure 2, velocity specific volume outlet u. Okay, so this is the sample of throttling valve. So here we call it as a adjustable valve. So here we call it as a porous plug. Here we call it as a capillary tube. Okay, so sample problem 3.19. Sample problem 3.19. Steam enters a throttling valve at 8 megapascal and 300 degrees Celsius and leave at a pressure of 950 kilopascal. Determine the final temperature and specific volume of the steam. Okay. 19. We have a throttling valve. So throttling valve, inlet, outlet. Okay, so at P1 8 MPa, T1 300 degrees Celsius, okay, and P2 is 900 kPa. Okay, final temperature T2 is to be determined. Okay, so basically here, as we are dealing with throttle valve, H1 is H2, same enthalpy at throttling valve. Okay, so state 1, final temperature T2 is to be determined. State 1, so the relation is on the enthalpy. So find first your enthalpy. So from this equation, so Add mikpasal. Check what is your Tsat. If 300 degrees Celsius is higher than Tsat, it's in the superheated. Or if your Tsat is same with T1, you got your mixture. If Tsat is lower than T1, so it's a superheated. So as we cross check that it's in the superheated. Check, this is a steam. So basically it's in the steam table lah. Okay, so superheated. So H1. Okay, state 2. Okay, so P2 is 900 kPa. H2 equal to H1. This is kilojoule per kg. So from here, from this value 2 point, we can interpolate the value of your temperature. Okay. Okay, so where is the condition? Okay, so check at 900 kPa. At 900 kPa, what is your Hg? Hg value. If your H1 is more than Hg, is in the superheated. As H1 is less than Hg, is in the mixture. So as H1 is less than Hg, so this state condition is in the mixture. So you need to determine what is the ratio or the fraction, the quality of the mixture, where your X percentage is H2 minus HFG. So what is your value of X? So from this X, okay, before S is in the mixture condition, directly Tsat, that is your T final. Ini mixture Tsat. Okay, so the fraction. Okay, from here also we can have the fraction. How much is also H2 HFG. Also we can determine what is the value of specific volume. So V2 minus VF2 over VFG. So V2 meter cube per kg. Alright. Okay, thank you. Mixing chamber. So mixing chamber is the section where the mixing process takes place. Mixing chamber does not have to be a distinct chamber. So it's only a ordinary T elbow or Y elbow in the shower, for example. serve as the mixing chamber for the cold and hot water stream. The conservation of mass principle for a mixing chamber required that the sum of incoming mass flow rate is equal to the mass flow rate of the outgoing fixtures. So inlet is equal to outlet, the mass flow rate. So the conservation of energy equation is analogous to the conservation of mass equation. So as we assume also, your heat is not generated, well insulated, so the Q is 0, and negligible potential and kinetic energy. So the general equation for mixing chamber, we take out Q and work. So also the kinetic and potential. So we have this equation only. So we have mass in and mass out. Sample problem 3.20. Sample problem 3.20. Consider an ordinary shower where hot water at 60 degrees Celsius is mixed with cold water at 10 degrees Celsius. If it is desired that a steady stream of warm water at 45 degrees Celsius be supplied, determine the ratio of the mass flow rate of the hot to cold water. Determine the ratio of mass flow rate of the hot to cold water, and assume the heat loss from the mixing chamber to be negligible and the mixing to take place at a pressure of 150 kilopascal kPa. Alright, so we have problem 320. So we have a mixing chamber. Okay, so here we have two inlet, one outlet. So I'm classifying, this is 1, 2, this is your 3 outlet. So this is your inlet, this is your outlet. Okay, so given directly the water, hot water, 60 degrees Celsius, T1, 60 degree Celsius, okay, and the cold water, T2, is 10 degrees Celsius, and warm water, T3, is 45 degrees Celsius. Okay. Alright, so we have three parts. So 2 inlet, 1 outlet. Okay, so from here we need to do a energy balance. Okay, so energy in minus energy out is equivalent to energy change in our system. Okay, as change in system is negligible because it's a steady state. Okay, so energy in is equivalent to energy out. Same with general equation before this lah. Okay, but your energy in, we have 2 types. Okay, so no work, assume no work, no heat added or inlet or whatsoever, so no PE and KE. So we have only the mass flow rate and enthalpy. So we have the summation m dot Okay, so H1, okay, summation M1 plus M dot 2 H2 is equal to M dot 3 H3. Okay, I have taken out all this. Okay, so as the question is to determine the ratio of mass flow rate. Ratio of mass flow rate. Okay, so the ratio of mass flow rate is between the hot and cold, which means M1 and M2. Okay, so substitute into your general equation. So we remove one unknown into the reducing the number of unknowns. So basically we can have M3 is addition of M1 plus M2. 2 inlet, 1 outlet. Okay, substitute into your general equation. So you have M dot 1 H1 plus M dot 2 H2 is equals to M dot 1 plus M dot 2 H3. Okay, so take out the M1 and M2 into one general equation. So as assuming as y is M dot 1 per M dot 2, substitute into your general equation here and here, and total here. So we got y hy plus h2 m2 take out. Okay, and m1 take out. Okay, equal to y plus 1 h3. As in the question, the pressure inside the mixing chamber P is 150 kPa. Okay, and cross check the T sat at 150 kPa. How much is 111.35 degrees C. So the temperature inside the mixing chamber is much below from this saturated condition. So which means that is in the compressed liquid. So from this compressed liquid we can have H1 at HF at 60 degrees C, H2 HF at 10 degrees Celsius, kilojoule per kg. H3 HF at 45 degrees C, kilojoule per kg. Solving your y, general equation y h1 plus h2 y plus 1 h3. So y is equal to, that is your ratio. Okay, so which means that m1 is equal to y m dot 2. What is the ratio? So that is your ratio. Okay, thank you. Heat exchanger. Heat exchangers are devices that where two moving fluid stream exchange heat without mix. So we have a border here. So the fluid A and fluid B is not mixed, but the heat can be transferred. So the heat exchanger are widely used in various industries, and they come in various designs such as radiators and cooling tower. So as general, your heat is zero, which by there is no leaking from the heat exchanger. Is well insulated for this our control volume, but heat is transferred from fluid A to fluid B or fluid B to fluid A, but it's not leaking from the heat exchanger. So that's where we have your Q is zero, well insulated. And potential energy and kinetic energy will be negligible. So your total energy balance will be, you take out your Q and your work. So we have mass in, mass B in, we have two fluid, inlet, two inlet, and also the outlet A and B. Sample problem 3.21. Sample problem 3.21. Liquid sodium flowing at 100 kg per second enters heat exchangers at 450 degrees Celsius and exit at 350 degrees Celsius. The specific heat of sodium is 1.25 kilojoule per kg dot degrees Celsius. Okay, beware, the specific heat given is in units of degrees Celsius, so you advise not to convert the temperature to Kelvin because the specific heat is in degrees Celsius unit. Okay, we continue with the question. Water enter at 5 megapascal and 20 degrees Celsius. Determine the minimum mass flux of the water so that the water does not completely vaporize. Okay, completely vaporize, which means that T sat, neglect the pressure drop through the heat exchanger, calculate the rate of heat transfer. Okay, 3.21. Okay, we have a heat exchanger, so we have one in, one out. Okay, so what in, out. All right, so here is your sodium. Okay, this is your water. For sodium, okay, so m dot sodium 100 kg per second, T in sodium 450 degrees Celsius, T out sodium 350 degrees Celsius. Okay, water enter at, okay, so this is your point inlet. So P water is P1 is 5 MPa, T1 water is 20 degrees C. Okay, so here is the question has given directly neglect the pressure drop, so which means that at P2 water is 5 MPa and T as T2, T outlet, T out water, T sat as given directly is not completely vaporized, so T sat. Okay, alright. General equation. As we have 4 types and neglecting no work, no heat, and no potential and kinetic energy, so we have m dot sodium, H sodium 1 plus m dot water, H inlet water is equal to outlet m dot sodium to H2 sodium plus m dot water, H2 water. Okay, okay, so assuming no heat and leaking, so m dot sodium in is equal to m dot sodium out, and also m dot water in is equal to m dot water out. Okay, so rearrange the equation. So m dot water H2 minus water minus H1 water is equal to equivalent to m dot sodium H2 sodium minus H1 sodium. Okay, your general equation. Rate of heat transfer. Okay, so okay, so as sodium here we have m dot enthalpy, so we can convert into CPT. So m dot sodium Cp T2 minus T1 sodium. Okay, so we can notice what is your mass flow rate. Okay, state water. Okay, so at P1 5 MPa, T1 water is at 20 degrees C. So compared to T sat at 5 MPa, what is your T sat? Okay, so from here, if it's in the compressed liquid, so we can get the 20 degree. So H1 or is a mixture. So from steam table we can directly get H1 kilojoule per kg, and also from the steam table P2 5 MPa T sat. Okay, so basically as up to not completely vaporized, so we cannot get the Hg, because Hg means is a saturated vapor, see, all completely vaporized. So we have here is a Hf is equal to H2 kilojoule per kg. Okay, so we have H1 and H2, substitute into your general equation. So we got your, okay, Cp has been directly given, T2 and T1 for sodium has been given directly, temperature inlet and outlet has been given directly. Okay, so from here we can get m dot water is, okay, you can calculate. Okay, for Q, the heat rate of heat transfer is m dot water H2 minus H1 is also equal to m dot sodium Cp T2 minus T1. Either one, you have all the figures, so we can get your heat kilojoule per kg. Alright, okay, thank you. Combustion chamber. A combustion chamber is that part of an internal combustion engine, ICE, in which the fuel or air is mixed and burned. In general, it is an enclosed space in which combustion takes place. For example, diesel and petrol engine and jet engine. So this is the schematic diagram of combustion chamber that can be illustrated. So we have a fuel, we have calorific value C, CHV, calorific value. We have air, normally oxygen, mixed in the combustion chamber and then burned out. So the product will be combustional gases. So the rate of heat energy generated from the combustion chamber can be written as this, we call it as a QCC, heat being generated as combustion chamber, Q combustion chamber. So the efficiency of combustion chamber times the mass flow rate of fuel times your calorific value. Okay, so we have this equation is your normal heat produced in combustion chamber. So this is the example of combustion chamber for a Rolls-Royce turbojet engine, and this is a normal engine for motorcycle or car. We have this the combustion chamber here. Boiler. A boiler is a closed vessel or arrangement of vessel and tubes together with a furnace or other heat source in which steam or other vapor is generated from water to drive turbine or engine. It supply heat, process certain material, and etc. We have two types of boiler. First, we call it as a fire tube and water tube. What is a fire tube boiler? Fire tube boiler is any boiler for generating steam by passing hot gas and other combustible product through a tube. So we call it as a fire tube, and it must in water to chimney or uptake, whereby for water tube boiler is a boiler for generating steam by passing water in a tube. So we call it as a water tube through a flame and hot gases. So this we call it as a hot water tube boiler. So we have a water tube. So water in a tube. So this is your fire. So the combustion chamber will go through each part. Whereas for a fire tube boiler, fire is passing through the tube. Fire passing through the tube. So this is your water. So this we call it as a fire tube boiler. So for heat in boiler is the efficiency of the boiler times your mass flow rate of fuel times calorific value. So this is similar with combustion, heat combustion. So combustion chamber and a boiler. So we have two types, combustion and a boiler. So your Q heat in is equal to combustion chamber and combustion in a boiler. So this is the total heat being produced. Heat is similar, therefore your Q in is your mass flow rate of water. So outlet enthalpy minus inlet enthalpy. So as boiler does not produce any work, the steam turbine is producing work, we only focusing on the combustion. So basically boiler is only required heat. So heat in, no work in. Heat out we assume to be well insulated, so no heat leaking. So all the potential and kinetic energy is taken out, cancelled out. So we have, this is general equation. So as mass in mass out is similar because we have only one inlet and outlet, so we taken out. So we have Q in is your same mass flow rate times enthalpy out minus enthalpy in.